Hey guys, welcome to Module 4, which is all about correlations. We've kind of tipped our toes into the water with this by looking at scatterplots. So at least visually, you guys have looked at somewhat of correlations up to this point, but now we're going to talk about the statistical analysis, what null hypotheses are included in a correlation, and then we'll figure out how to interpret results when we actually run it in SPSS. We also will be working on how to create certain components of the correlation output in Excel as well, so you have multiple ways to calculate things that you might need. But as a recap, at the end of the last lecture we had, we kind of have gone through all of our foundational information, like what are the variables, what types of data do we have, how do we classify the samples that we're working with, and how do those sample collections pair with the types of independent variables that we have, that type of stuff, right? So we used all of this information then to kind of inform us what type of test we might use. So as a recap of that, right, usually we need to understand what type of variables we're working with. So do we have categorical or ordered variables, which we call non-parametric? In our class, usually these will be nominal. And then do we also have like parametric data, right, which is usually going to be categorized as our dependent variables, in which they are typically going to be ratio data, but could also be interval data, right? So figure out or classify your data based on the variables that you have collected is kind of step one. We also need to consider how many independent variables and dependent variables we have, who we're measuring, right? So usually these are going to relate to the independent variable, right? Do you have a within subject comparison where you're using the same subjects for each measurement that you've taken? Or do you have a between subject comparison or between subject independent variable, between subject factor? And there's all different ways that you could describe between and within subjects, right? The between subject one is going to say that you have independent samples that have been measured. So usually it requires like a control group versus an experimental group. Maybe you have multiple experimental groups, but in either case, between subjects is going to have a different sample for each of those groups. Okay, so who are we measuring? That's a big ticket item. This one isn't going to apply to our correlations and regressions for this week and next week, but it's still a good thing to review so it doesn't leave your brain. And then the last thing is, do we meet test assumptions, which we're going to start getting into this week. Each statistical test is going to have a different set of assumptions based on the calculations that are used to provide you with the output that you get in SPSS. So assumptions are very important. They differ for the most part between each test. But we put all of this information together and we get our decision tree, which tells us basically how we can get to a certain test based on different components of our research question and the sample that we've collected. We use all that to provide us with which test is most appropriate for the scenario that we're working with. So for this week and next week, we're going to be operating with parametric dependent variables as well as parametric independent variables. And those are going to lead us to correlations and regressions. So this week we'll focus on correlations, next week we'll focus on regressions. Both of them are very similar in nature in terms of like we're looking at relationships between variables. Correlations are purely looking at relationship versus regressions, which look at more of a predictive relationship and using relationships between variables to determine the outcome of a certain variable of interest. So we'll go into those a little bit more, make that a problem for another week. But for now, we're kind of just focusing on the correlation component. So I've put our decision tree, kind of cut out things that we don't need and put it into this nice flowchart for you. So usually for a correlation, we're not really going to have a defined dependent variable or independent variable. You can kind of keep that loose, because the relationship between variables is the relationship between variables. So it doesn't really matter if you define a dependent versus independent variable. When we get to regressions, that's when the independent and dependent variables should be defined, but again, we'll cover that in a different lecture. Generally speaking, though, the types of variables that you should have for your dependent and independent variables should be parametric, right? So you either have ratio or interval data. And then the goal of the test is going to kind of help split up if you're doing a correlation or if you're doing a regression. So like I said in the previous slide, correlations are purely going to be looking at the relationships between variables and if those relationships are significant or not, what the strength of those relationships is, what direction the relationships are in. The regression is going to use the correlations to predict the outcome of a certain variable. So that's the main distinction between the two. We're going to just focus on this top part for this week. Just to give you guys an idea of what correlations do, I'm sure most of you have been exposed to a correlation at some point up until now. But correlations quantify the degree of the relationship between variables. And we can have different types of correlations based on the number of variables we're comparing. So a bivariate correlation is bi meaning two, you have two variables. Generally, we can say this is an independent or an x variable and a dependent or a y variable. Okay, so again, it doesn't matter in a bivariate correlation really which variable is your independent, which is your dependent. More often than not, like in the activity, I will specify which one I want you to plot on the x-axis versus which one I want you to plot on the y-axis. But when you set up your test, the answers are going to be the same in the output. So, like I said, it doesn't really matter how you define your independent and dependent variable for correlations, particularly. If you have multiple comparisons that you're going to look at, that's called a multiple correlation, which is convenient in terms of terminology. But in this scenario, typically we say that we have more than one independent variable and we want to see how that is related to the dependent variable. All you guys really need to know, again, is you just have more than two variables that you're interested in looking at the relationships for. In a multiple correlation, what ends up happening is we just do a bunch of bivariate correlations and we put them in a table. So again, defining an independent versus dependent variable isn't that important for a multiple correlation. We also can have partial correlations, which we don't really cover in this class because they get a little bit complicated, but partial correlations are going to be an integral part in determining regression formulas and models, which again, we'll talk about next week. But generally speaking, this is when you have more than 3 or more variables, right? So you could have 4, you could have 10, you could have 100, but you have multiple variables that are contributing to some degree of variation to a dependent variable, usually. So we're looking at how do different components in our analysis, usually the independent variables, how do all of those contribute to a dependent variable? And what is the degree of contribution that each of those independent variables contributes to the outcome of the dependent variable? So that's kind of the goal of a partial correlation, is you're looking at relationships between variables while excluding other variables. Correlations, at least the types of correlations that we're doing in this class, are going to be Pearson's product moment correlation coefficients, or you can just call them Pearson correlations. And the coefficient that we use to identify both the strength and the direction of our relationship is R. So some of you may have seen R before, but R is going to be the coefficient that we use to kind of equate what the strength and direction of our correlation is. We can use Pearson's correlations for linear relationships only. We'll discuss what linear means in further slides in the presentation. But R has values that can range anywhere from -1 to +1. +1 is going to be a perfect positive correlation. -1 would represent a perfect negative correlation. 0, which is the midpoint between these two, indicates that there is no relationship. So what these values mean in addition to the direction we'll go through in some later slides, but this just kind of gives you an idea of what values could be assumed by your correlation coefficient R. I do want to point out that the numerical size of R, so 1 versus 0.5 versus 0.37, right? The actual numerical value is going to be the strength of the correlation, whereas the sign is the direction. Okay, so when we're looking at a negative correlation, that does not mean it's less than a positive correlation. It just means that the relationship is in a different direction or an inverse direction. So why would we want to use a correlation? Typically, we're going to use them when we want to establish unknown relationships. So correlations are often the first stepping stone that we might use to inform hypotheses or to inform us on what cause and effect relationships we might want to look at in future research. Okay, but we can figure out how different variables are related to each other, figure out if there potentially could be a confounding variable, and that might inform our inclusion-exclusion criteria, etc., etc., etc. So correlations can be really great as a part of foundational research to inform us on decisions we should make in cause and effect research. We can also use it to validate different protocols or equipment. So the example I give here is if we were measuring body composition or a person's percentage of body fat, and we use skin fold measurements versus bioelectrical impedance. The outcome that we actually get would be the percentage of body fat that a person has. And then we can use a correlation between those two measures to see how similar they are. Right? The more similar our outcomes are, the stronger the correlation. We might also want to see how well a test can predict performance. This is a method called cross-validation, and we'll actually do an example of this next week when we look at the outputs of regression equations. So again, regressions are going to be used to predict a certain variable outcome, and then we can compare, right, if we have a bunch of different regression equations or models that we're using to predict this outcome given its relationships with other variables, we can say how well do these outcomes match. In other words, or how well do these outcomes match to the actual data measured. So we're comparing actual collected data to the model produced data, and then we see how well do those actually match together. Again, the stronger the correlation, the better the model is. So we'll go through examples of this next week that will end up making a lot more sense later down the road. I do want to point out, though, that correlation does not prove causation. And this is a comment that I've made on some of your activities or exams when we were looking into our hypothesis testing and creating null hypotheses. And I told you guys, make sure you take note if we're looking at an effect versus a relationship, because relationships are just saying how likely is one variable, or how likely are we going to get an outcome for one variable based on its relationship with another variable. Okay, so that's the relationship aspect. Effect or causation, cause and effect, is the outcome of this variable is due to the effects or manipulations of another variable. We can't necessarily say that with correlations. We can only say this is the relationship that exists, but we can't say that one variable caused the outcomes of another one. I have some examples on this concept because it is quite important when you're interpreting results from a correlation. So I've chosen to have a variable IQ, and I want to see what its relationship is to GPA. Okay, so I feel like it's pretty reasonable to say that a person who has a higher IQ usually is potentially could have a higher GPA, right? However, there are other factors that could play a role in the outcome of GPA. Right? So GPAs are, generally speaking, it's our dependent variable of interest, and IQ would be an example of an independent variable if you were distinguishing the two. Okay? But again, the relationship that I see with these two does not necessarily mean that having a high IQ causes a person to have a high GPA. Right? There could be other factors such as a person's motivation in school, what their study habits are, if they have financial support, right? Because for most of you, if you're paying for your tuition or, paying for rent while going to school, so if you're living away from home, generally speaking, if you don't have, grants or scholarships, you have to have a job. And how much time you put into work outside of class could impact how much time you actually get to study for a class, which could end up influencing your GPA, right? We'll also have the amount of study time. So how a person studies versus how long they study could both impact a person's GPA. Who the instructor is. Sometimes you have a bad teacher who doesn't explain stuff to you, right? And they could, if they're not teaching the subject material well enough and you're doing independent learning instead, then that could also impact your GPA. And then there could also be parental pressure, right? This is not an exhaustive list of variables that could affect GPA. It's just to kind of give you the idea that we can never say that a relationship proves that there is a cause and effect between two variables, because there are more players that need to be considered. Another example that we could also use to explain that correlations do not prove causation is between leg length and pant length. Okay, so typically you would expect a person with long legs should have longer pants, right, or the longer part of the legs in pants. And generally speaking, we could go the other direction and say that longer pant lengths are usually going to be associated with people who have long legs, right? But we're looking at an association. We can't, however, say that if we have people, or if we have long pant lengths, that does not cause a person to have long legs, right? So that's where the cause and effect thing. You can't just magically grow your legs because you have long pants. That would kind of be cool, but it's not true. So while a relationship does exist between these variables, we can never say in a correlation that one variable causes the outcomes of another variable. Okay, now we're going to get into what the direction and the strength of our correlation coefficients are. So we've kind of gone through our foundational basic information, and now we're getting into the math part of things. So recall that our R coefficient can range from -1 to +1 with 0 in the middle. And we said that the numerical value of R tells us the strength of the relationship. The positive and negative sign are going to tell us the direction. So a positive correlation is going to usually assume the shape of, and in this class we're doing linear correlations, it'll assume the shape of kind of a linear or a line that has a positive slope. So the positive part is the slope of the correlation, or the slope of the line of best fit. And generally speaking, I've got these correlation coefficient values that we would use to determine the strength. So if we have a perfect correlation, that's going to assume a value of +1. And that's where if for a given x value, we get a y value. And then if we keep increasing x, we keep getting a proportional increase in y. So the more aligned your data are, or the more they represent a line, the stronger the correlation is going to be. So when we have a correlation coefficient of 1, we call this a perfect correlation. This doesn't typically happen out in the real world, so anything between 1 and 0.7 we usually say has a strong relationship. So you can see in this graph, right, as if we look at the cluster of these scatter points in the plot, right, they generally represent a line in which we can interpret as x increases, y also increases. As we go to moderate and weak correlations, you can see that these scatter points become more loosely associated, but we can still generally see that there's an upward trend. Okay, so moderate correlations will associate with R values that are between 0.7 and 0.3. Weak correlations are usually going to be R values that are less than 0.3. The same associations can go for negative correlations, but instead of having a proportional increase in x to y, we're going to have one variable decreasing as the other one increases. So in this case, we have x increasing with proportional decreases in y. So that would give us, if it's perfectly proportional, then we have a correlation coefficient of -1, or a perfect negative correlation. And then similar to our positive correlations, as our scatter points become more loosely associated to each other, that means our strength of our relationship is weakening. But we can still see that they have this downward slope, or a downward trend in which as one variable increases, the other one decreases. The values of R that we use are going to be the same, because remember, strength is determined by the value of R. The direction is determined by the slope of the line, whether it's positive or negative. We could also have an instance where we'd have zero correlation, or where the slope is 0, right? So this is usually when we've got a bunch of scattered points in a scatter plot, and we don't really see an upward trend or a downward trend. They're just kind of randomly dispersed. When we have a line, or a best fit line, that is horizontal, that has a slope of 0. Slopes of 0 mean that a relationship is undefined. So if we add a trend line to our scatter plots, usually the more horizontal that line is, the weaker the relationship is between the variables. The more the slope or the line represents kind of an upward linear, like 1 by 1 trend, or a linear down 1 by 1 trend, that'll be indicating a stronger relationship. So I keep mentioning scatter plots, and those are the best way that we can observe relationships between two variables. We can apply a line of best fit, which in Excel it's a trend line, but that's going to be the best linear estimate of the relationship between the variables that we're looking at. And basically there are ways that we can calculate where this trend line goes. And we talk about this a little bit more next week, but the way that the trend line is placed in the graph is to minimize the amount of error that exists between each point and the line of best fit. So usually the softwares that we have are able to do this for us, but you can see that the line should relatively be going through the center of the data.